All right, here we are. Well, the weather didn't turn out to be that awful, but that's okay. It's nice to be online once in a while. It certainly saves a lot of traveling time, doesn't it? What we have to do here is we're going to go finish up reviewing for the sample midterm. And then I guess we'll just dive back into chapter 6, which we'd started once before, but we had to put it aside, of course, to review. So first, let me go get our information. We'll go to Blackboard and download our notes. So first, we need the sample midterm, which we'd already started. And we did go over a fairly large percentage of it, but we're not quite done. If I remember correctly, we did all the fill-ins and some of the problems. Let's see, we had all these problems. Let's see. Oh, that's right. I remember now. Yeah, we got up through 4 with the sample space and the where we had the coin flip 3 times. Okay, so we'll pick it up from here with number 5. And when that's done, I don't think this will take up the rest of the class. We'll just carry on and at least take a peek at chapter 6. So then next week, we'll be back, hopefully to normal. We'll be back on Tuesday in person. And then next Friday, the 4th, we'll have the actual test. Okay, so that way you'll have time if you want on Tuesday to ask questions about what we're doing here. And wait a minute, hold on. Yeah, so you can ask any last minute questions that you have, and then we can have the test a week from today, which is March the 4th. All right, that sounds good. So we have plenty of time. There's no hurry. Let me just do something real fast. All right, here we go. So let's take a look at these. Number 5. So what do we know in number 5? Well, a card is chosen from a deck. The card is then replaced and the second card is chosen. Now the key detail there is that the card is replaced. So that when we pick the second card, the first one is back in the deck. Yes, I'll be posting all the solutions as soon as we're done. Okay. Now, I already have them typed up, but I want to go through them with you as if I were writing on the board too. So you'll have everything we did available to you as soon as we're finished. Good question, though. Yes, I will not forget. We'll probably have to wait till tonight, but I'll definitely be posting them. All right, anyway, so when the card is replaced, the entire deck is intact when we pick the second card. So that's a hint that A, where we pick the event that the first card is a king, and B, the event that the second card is black. Because of sampling with replacement, we already know that A and B are independent of each other. Okay, that's enough for us to know that the two are independent. The fact that the sampling was done with replacement is enough to tell us that whatever happens in the first card does not affect the second card. So just as a quick review here, I've reminded you that a standard deck contains 52 cards, half are black, half are red. And there are, of course, 4 kings in the deck, 2 of which are red and 2 of which are black. We have the red ones are the king of hearts and the king of diamonds. And the black ones are the king of spades and the king of clubs. All right, so if it's been a while since you played cards, I just want to make sure you haven't forgotten how that works. All right, so how about the probability of A? Well, the first card is a king. Well, that's easy because there are 4 kings in the deck out of 52 cards. And that's it, you're done. I mean, if you want to reduce this to 1/13, you can. But that's the answer. And then because we know that when we picked the second card, the entire deck was still there. So the second card being black has a probability of 26 out of 52. And by the way, if you notice, we're implicitly assuming here that all cards are equally likely to be chosen. So we have a sample space, which is the deck, where each outcome is equally likely to occur. So if I pick a card, any card, it's just as likely to be the ace of spades as the seven of spades or three of hearts or whatever the case may be. If there's some reason why they had different amount of probabilities, we would have to do something a little different, but that's not the case. Each card is equally likely to be chosen. So that's why we can use this approach. All right, so now we can start using the rules. For example, this one is simply 1 minus the probability of A. 12 out of 13. Or if you left it in 50 seconds, that would be 48 out of 52. Very good. How about D? Same thing, it's a complement. The complement rule is very straightforward. And here's just 1 minus a half, which is a half. Or if you want to write it as 26 out of 52, that's fine too. All right, so far so good. Now A and B. Now this is interesting because you might recall that the multiplication rule is applied to the probability of an intersection. But we already know that A and B are independent of each other. And so therefore we can feel free to use the simplified multiplication rule, which tells me that this is simply equal to the probability of A times the probability of B. Since A and B are independent due to the fact that the cards are chosen with replacement. That being the case, I can just write them out. I can multiply them directly together, 1/13 times a half, 1 out of 26. And that's it, we're done. But the trick was that knowing that these two events are independent of each other, so we can use the simplified version. Okay. Now, how about these? A given B and B given A. These are the so-called conditional probabilities. And here, what we need to do is write out the definition. And then we should already have these probabilities from earlier. So, for example, here we have 1 out of 26 over 1 out of 2. Now, algebraically, this is the equivalent of 1 out of 26 times the inverse of what's in the denominator, or 2 over 1. So this ends up being 1 out of 13. Now, logically, when you think about it, what this is saying is that we pick a card. Well, all right, anyway, it's fine the way it is. We don't have to think about the logic behind it. It's just be aware, though, that this requires us to know the intersection between A and B. And by the way, I do want to point out one interesting thing. Because, and you didn't have to know this to get the question right, but I just want to point this out. You might recall that independence, if A and B are independent, then two things are true. The probability of A given B equals the probability of A, and the probability of B given A is the probability of B. So what we could have done was simply said the probability of A given B equals the probability of A, which we previously calculated to be 1 out of 13. And so you, instead of using the formal definition of A given B, you could have used this to do the same thing. But That's up to you, but I just wanted you to notice this. Okay, so in other words, yes, you probably should write out the definition, but in a case like this, it isn't absolutely necessary because, you can see due to the independence, and here's the same thing. It's just going to equal whatever the probability B is. But why don't we show it with the definition? So remember, A and B has a probability of 1/26. A was 1 out of 13, right? And so that's 13 out of 26, which is a half. But you might recall that we do know these are independent events. So therefore, the probability B given A is the probability B, which we already know from up here is a half. So we've got two alternative ways of getting to the same result. Very good. Now, are A and B mutually exclusive? Why or why not? Well, they're not, because the probability of A intersect B is not equal to 0. In fact, we've already seen that it's equal to 1 out of 26. So therefore, the answer is no, because the probability of their intersection is non-zero. Now for this one, we can just simply say yes, because the cards were chosen with replacement. Or we can just demonstrate that, as we said before, we can do it this way. And so, we know, for example, the probability of A given B from earlier was 1 out of 13. And the probability of A is 1 out of 13. The probability of B given A is a half. And so is the probability of B. So both of these conditions are met, but it might be a little quicker to just note that the cards were chosen with replacement, fine, they're independent. But if not, we can use this approach, which is what we normally do. Okay. Now, are they complements? Well, that's a different question altogether. For A and B to be complements, it must be true that, okay, there's two conditions here that have to be met. The probability of A and B, or A intersect B, must be 0. And their union has to be 1. But this is false. We already have seen this. They are not mutually exclusive. That indicates that A and B are not complements. And that's all you have to show. One of the conditions is false. We could try the other one too, but it doesn't matter because the first one is false. And that's it. That's all we needed to demonstrate that A and B are not complements. All right. Now, how about this one? Now here, this one is interesting because we're not given any real information about where these probabilities came from. We know what they are. We don't know what the sample space is. We don't know how they were generated. So all we can really do here is use the. Okay, so for example, here, we have the complement rule. One minus 0.2 is 0.8, end of story, that's it. How simple is that? 1 minus PB. How easy is that? 1 minus 0.5 is 0.5. Now for the union, we're going to use the addition rule. Okay, so we have everything we need. 0.2 plus 0.5 minus 0.2. 0.5, that's it. Okay, now we can do the same thing with the conditional probabilities. We're going to use the definition. Point 0.2 over 0.5 is 0.4. All right. Now, we're going to do the other conditional probability. So we have 0.2 over 0.2. All right, well, that obviously gives us 1. All right. And now we have the conceptual questions. Are A and B mutually exclusive? Well, the answer is no, because the probability of A and B is not 0. All right, remember up here, it showed us that that was equal to 0.2. What about independence? Well, we've got 2 things to demonstrate. And of course, it has to be both of these. So we're going to go get the probability of A given B. And remember, that was shown to us as, we calculated as 0.4. The probability of A, if you recall, was 0.2. Well, they're not equal, are they? Since the probability of A given B is not equal to probability of A, it shows that A and B are not independent. All right, beautiful. And then again with the complements require that the probability of A intersect B is 0. And their union is 1. But we've already seen that the probability of A given B, or sorry, A and B, is 0.2, I believe. Yep, 0.2, which is clearly not 0. So since this is not 0, A and B are not complements. Beautiful. All right, now we have one of our tables. This is a joint probability table for coffees again. That's kind of an easy example to make up probabilities for. So let me split the screen so you can see everything. All right, so what do we want to know? All right, F and D, that would be decaf French roast. That one we can literally just look it up. At the intersection of F and D, 0.18. About this one, R and E, regular espresso, 0.10. R and G, regular Guatemala, 0.12. F is the sum of both French roasts, 0.46. R is all of the regulars over here, 0.5. D, complement is 1 minus the probability D. And D itself is right here, 0.5. F or G, now remember, these columns are assumed to be mutually exclusive of each other. So we can use the simplified addition rule and just add up the French roasts and the Guatemala. You get 0.68. This one would be Guatemala's plus the espressos, which means 0.22 plus 0.32, 54. Now, these are, of course, the conditional probabilities. So we'll write out the definitions. DNF is decaf French roast, 0.18. F is the total of the French roasts. So therefore, what we're going to see here is whatever that ratio is the correct probability. 0.18 divided by 0.46, 0.3913. All right, now. How about R given E? So the numerator is regular espresso over here at 0.10. E is espresso. The total of all the espressos is 0.32. And so that's going to leave us with 0.3125. And then we have one more, G given R. So in the numerator, we have G and R over PR. G and R is Guatemala regular, 0.12. Regular across here, the total is 0.5. So that's 0.24. All right, so those are done. And now, oh boy, look at this one. This appears to be a Bayes theorem question. Oh, I was afraid of that. Yeah, you can tell by all the writing. So what do we know here? If the economy recovers next year, the probability that the price of stock X will rise is 40%. If the economy remains in recession, the probability drops to 10%. Now, those are conditional probabilities. We'll save those for last, okay? The other two are the unconditional probabilities. The probability of recovery, 0.30, and the probability of recession is 0.70. So how do we visualize this? Well, we have a sample space, and the sample space is broken up into recovery and recession. Okay, how can you tell? Because those probabilities add up to 100%. So let's draw a little picture. So let's say A1 is the recovery. And A2 is the recession. The probability of A1 is 30%. The probability of A2 is 70%. Now, the other event that's mentioned here is the stock price of X going up. That is what we're going to call B. Okay, so we will not have a probability for B. What we will have is conditional probabilities where we're being told what the probability B is depending on whether we're in a recovery or in a recession. So if you read these carefully, they're giving us both of these, the probability B given A1 and the probability B given A2. A1 is a recovery. So it says right there, if the economy recovers, hold on. If the economy recovers, the probability of the price of stock X going up is 40%. That would be this one. Because A1 is the recovery. If we're in a recession, the probability drops to 10. That's this one. A2 is recession. In a recession, the probability that stock B goes up, stock X rather goes up, is 10%. Now, just as a double check, these have to add up to 1. These do not. They might, you don't have to. So if you got these backwards, this is one way you would know it, because these would not add up to 1. So that's how you can keep your eye out for that. Now, what is the actual question though? If the price actually goes up, what is the probability that the economy is in recovery? So this is also a conditional probability, but this time we're being told that the price went up. And with that information in hand, what is the probability of being in a recovery? That's what we're being asked to calculate. Now, this is where we need Bayes' theorem. And so the way it works is this. Now there's a formula. And in fact, it's on the formula sheet for the exam. Actually, let me fix this. So while we're at it, let me go back here and see if I can, oh, you know what, I may not have posted it. No, there it is, there it is. Here we go. I'm just going to copy this. Man, this is so convenient. I can't do this on the board, that's for sure. All right. Oh. Okay, so what we have to do is recognize that in the denominator, we're always going to have all the possible A's listed here. The numerator just has one of them. So in other words, the probability of A1 given B. Now here, these I's refer to this one. P, B given A1 times the probability of A1. In the denominator, we're going to add up all of these. Now, in this case, there's only 2 A's in this diagram. So we only need two terms in the denominator, which will be B given A1 times A1 plus B given A2 times the probability of A2. Once you got this straight, the rest is just substitution. All right, so let's do this. Let me first split the screen so we can see everything. All right, okay, here we go. All right, so we're going to have B given A1 is 0.40. A1 is 0.30. Then we have the same numbers. This time, though, plus 0.10 times 0.70. All right, and what is that equal to? Hold on 1 second. Just trying to get everything lined up. So we're going to have 0.12. And then here we have 0.07. So that's what we're looking for. So whatever that ratio is, 0.12 over 0.19, 0.6316, let's say. Okay, so that's what you have to do now. So the challenge here is setting it up properly, really. First of all, get comfortable with this formula. And secondly, make sure you can identify which are the unconditional probabilities, the A's that is, and which are the conditional probabilities, which refer to stock X rising in this case, based on the state of the economy. Once you have all that set up, then you're basically just plugging away. All right, it's a very complex problem, but once you get used to it, you can see that it's pretty much always the same. This is the challenge right here, right up here, getting this right. So you have to be careful with the way you read this information. Identify which of these are conditional probabilities, like these, and which ones are unconditional probabilities, like these. Those give you the values of the A's. These give you the values of the B's given A1, A2, A3, etc. All right, so that was that. Now we get to go back to chapter 6, it looks like. Now it's been a while so we may have to review a little bit. Chapter 6 is where we started looking at probability distributions and random variables. So I think I remember that we introduced the basic concepts, but we never quite got around to our first example. So let me get those open. Let's see. Yeah, here we go. Chapter 6. All right, so we're going to look at what are called discrete random variables. But before we did that, we introduced the concept of the random variable and the probability distribution. And in examples we used, at least, they were really not very complicated, but they can get very messy in a hurry. So what was a random variable? Well, first of all, whenever we have a random experiment, there are always some kinds of outcomes taking place. They could be heads and tails, they could be evens and odds, they could be all kinds of things. But ultimately, what we really care about is numbers. So what will happen often is that we'll assign numbers to the outcomes of an experiment in a very specific way. For example, when we roll the die twice, remember we had 4 possibilities, EE, EO, OE, and OO. If we're interested in evens, then we might define X to be the number of evens that turn up during the experiment, which means that each point is assigned a value by X. So in other words, when we have 2 evens, X is 2. When we have EO or OE, X is 1. And for OO, X is just 0. That's pretty straightforward. We're taking all the actual outcomes and turning them into X's. Now, having said that, that's fine as far as it goes, but ultimately what we care about is probabilities. What we can do now is calculate probabilities for every possible value of X. So for example, the probability, remember, these are all equally likely to occur. So the probability that X equals 0 is equivalent to saying, what's the probability of getting OO when we carry out this experiment? And because they're all equally likely, that would be 1/4. Okay, you can rewrite that as 0.25 if you want to, but that's how we do it. Now, when x equals 1, there's two things that can happen that cause x to equal to 1. We can either get an EO or an OE, which means that the probability of 1 is not 1/4, but 1/2 or 2/4. And then finally, for x equals 2, that can only happen one way, which means both are even, and that probability is 1/4. So what we basically have done is taken a table like this and assigned probabilities to those x's, and that is what we mean by a probability distribution. So actually, let me just draw it in here real fast. Like we did on the board, we had x's and we had probabilities. 0, 1, 2, 1/4, 1/2, and 1/4. This table is a probability distribution. X itself is a random variable. And that's it. That's what this is all about. Now, of course, all the cases we'll be looking at will be more complicated than this, but this is, in a nutshell, what a random variable is and a probability distribution. A couple of important things to note about these. First of all, the probabilities are all non-negative, and all of them have to add up to 1. All right, so in other words, you can't have a negative probability, you can't have one that goes over 1, and they all have to add up to 1. Otherwise, they violate one of the axioms of probability, and therefore this would not be a valid probability distribution. So you have to keep an eye on that, but that's what is required for these to be probability distributions. Now, when it's the case, like we have here, that x can only assume a finite number of values, 0, 1, and 2, for example, we call that a discrete random variable, to distinguish it from the opposite case where we can have an infinite number of possibilities, which we call a continuous random variable. So finite means discrete, continuous refers to an infinite number of possibilities. Okay, oh, here it is. It was already here. This is our probability distribution generated by that experiment we just carried out. The x's assign numbers to the actual outcomes, EE, EO, etc. And on the right-hand side, we have all the probabilities. All right. Now, I think we did get to this point. We remember from an earlier chapter that a sample or a population can be described by one of these special measures. We have measures of central tendency like mean, median, and mode. We have measures of dispersion like variance and standard deviation. And then we had the measures of association, which were the covariance and the correlation. We have something similar to that for random variables, but the names are slightly different and the formulas are different too, because they have to take into account the fact that here we're dealing with probabilities, whereas we don't have probabilities with a sample or a population. So, and also the names are different. Instead of calling them measures, now for some reason, they're called moments. So we have to get used to this. You know, there's always going to be several comparable concepts that may have different names in statistics. It happens all the time. So when we're dealing with random variables, these measures are now known as moments. So we only actually introduced 3 of them, although we can certainly do more of them if we want to. But for our purposes in this chapter, we're only going to focus on the 3. Okay. And so the first one is the expected value, which is just another name for the mean. And then, of course, we have the variance and the standard deviation. Now, the question is, what do these formulas look like? And how do we interpret them? Well, the expected value is the average. Sometimes you don't have to know this. It's sometimes called the first moment. And what we're doing is we're creating a weighted average where the probabilities are the weights. That's really what this is all about. It's a weighted average of the x's where the probabilities are the weights. So you're basically just multiplying each x by its own probability. You add them up, and what remains is your expected value. So let's do an example using that last case we just had. Here's x. Let's think of this as the first x. How about x1, x2, and all right, so we substitute in the numbers. 0 is multiplied by a quarter, 1 is multiplied by a half, 2 is multiplied by a quarter. We add these up. And we end up with 1, which means on average, if we roll the die twice, we should expect to get one even number. We don't always get 1, but on average, we should get 1. The variance. Now, the variance here is the same concept as what we had in the previous chapters when we applied it to samples and populations. It basically is a measure of how spread out the data are from the center. The formula is going to be a little messier, but you can see it's very similar in a lot of ways to what we did in chapter 3. You're basically finding out how far each x is from its own mean or expected value. We square the result and multiply or weight that by its own probability. Now, in this case, the expected value of x was 1. So you're basically subtracting 1 from each value of x, squaring the difference, multiplying by the probability, and adding them up. Okay. So here's x1 minus ex squared. Then we have and then I'm running out of space. This last one is x3 minus ex squared px3. So when we go through all the calculations, we get a variance of a half. It's kind of hard to interpret the variance. Mainly, and just like with the samples and populations, we're really interested in the standard deviation. And just like before, we just find out by taking the square root of the variance. Okay, that part hasn't changed. All right, and the good thing about the standard deviation is that it's measured in the same units as the underlying data, unlike the variance, which is measured in squared units. All right, so we write that as sigma. It's the square root of the variance. And so we take the square root of a half, and here we are, 0.7071. All right, so that's enough reviewing. Now let's look at these discrete probability distributions. There's two that we want to focus on because they're so heavily used in statistics for business applications. And so I'll show you their names, and then we'll introduce them. And what will happen here is that it'll turn out that each of these cases has its own unique set of formulas for calculating not only the probabilities, but the moments. Okay, well, let's start with the list. We have the so-called binomial distribution, and then we have the Poisson distribution. Now, Poisson, you can't tell from the name what it means because it's named after the inventor, but binomial, the name is kind of helpful in figuring out what's happening. So we'll see that in a second. Just remember the prefix bi means 2. And that's a hint as to where this is going. Now, in order for us to use the binomial distribution, we need to use a special type of random process or experiment to generate our results. So, it's not the case that anything goes. What do I mean by that? Well, imagine the following situation. Suppose that in our experiment, we have n trials, like rolling a die, flipping a coin, whatever. But here, it must be the case that, first of all, each trial is independent of the others. Otherwise, this is not the binomial distribution. Number two, each trial can only have two outcomes, success and failure. Now, which one is success and which is failure, that's up to us to decide. But there's only two possibilities. And this is why this thing is called binomial. Okay, now, by the way, there does exist a distribution for three outcomes, and it's called trinomial. We won't be doing that in this class, though, because it's very complicated. Instead, we'll stick with the binomial distribution. Now, what's the third requirement? The probability of getting a success on a single trial, which in this book is designated with the letter pi, must be a constant from one trial to the next. If all these conditions are met, then this is a binomial experiment. And if it is, then X defined on this experiment as the number of successes that occur during n trials is now defined as a binomial random variable. It's not just any random variable. It is a special case known as a binomial random variable. It is uniquely characterized by the number of trials and the probability of success on a single trial. Okay, so X is now officially considered a binomial random variable, which means it has special properties, which we can take advantage of. In other words, it'll make it possible for us to have relatively straightforward formulas in order to calculate the probabilities that we need. Okay, or you can also say that X is binomially distributed. It means the same thing. X is binomial, or it is binomially distributed. If that's true, there's a special formula we can use to calculate any probability we need for X. All right. In other words, we don't have to sort through the entire sample space and figure out how many times something happened. Instead, we can use a formula, but the formula itself is a little bit challenging. So what we have to do is take a look at it and then go through it and break it up into its component pieces and try to understand what each one means. All right, so first of all, here's the formula. Now, the only part that's really the least bit tricky is here. What does this thing mean? This term is actually a shortcut. The others are straightforward. We have pi to the x power, 1 minus pi to the n minus x power. And remember, n is the number of trials. X is the number of successes. And then finally, pi is the probability of success. So what is this thing? Good question. It's a shorthand for something else which you may or may not recognize. Let's find out what that is, and then let's see if it looks familiar at all. All right, here we go. Oh, now that may not be helping you at all. This is what it stands for. And these exclamation points are pronounced factorial. So that means n with this exclamation point is pronounced n factorial. But what does that mean? Okay, and of course that also implies that x with a little exclamation point is x factorial. All right, so this is actually a mathematical operator. If you look in your calculator, you should be able to find a button labeled x factorial that will give you what you need, but this is a very interesting mathematical operator, and here's what it says. It starts with 0. Now, this thing is only defined on non-negative integers. So how does it work? Well, the first two are easy. 0 factorial is 1. 1 factorial is 1. Then it gets interesting. 2 factorial, look at that. 2 times 1, which is 2. 3 factorial, which is 3 times 2 times 1, which is 6. 4 factorial, 4 times 3 times 2 times 1, 24. And so you kind of get the idea now. For example, 5 factorial would be 5 times 4 times 3 times 2 times 1. Now, what exactly does that tell us? Here's an interesting application of the factorial operator. Imagine the following situation. You've got room on your wall for 3 posters. You own 3 posters. You just moved into your room and you've got 3 posters and you want to hang them up. There's enough room for 3 posters. Those are them. You've got a poster for Yankees, you've got a poster for Salvador Dali, and you've got one for statistics, of course. How can you hang them? Well, let's say, remember, we're assuming the wall only has room for 3 posters. So what we're going to do here is list them all. You can have Yankees followed by Dali, followed by statistics from left to right, or you can see you could try reversing these two. You could have Yankees, statistics, and Dali, and you can see all together, if you go through the list, there are 6 different ways of hanging your posters. That's it. We covered all the possibilities. So with 3 posters, there are 6 ways of hanging them. And in math, each of these ways that we hang the posters is known as an arrangement, because the only thing that changes from one to the next is the sequencing from left to right, or the order in which I hang them. Each one is known as an arrangement. Now, it turns out that the number of ways of arranging any number of objects, n, is equal to n factorial. So all of a sudden you see why this is so important. So that implies that for 3 posters, n is 3, there are n factorial 6 ways of hanging the posters, which is the same thing as saying 6 arrangements of the posters. So you don't have to actually write them all down. All right, so like here, I did, just so you can see them, but with 3 posters, there are 3 factorial ways of hanging them. each way we hang them is called an arrangement, because all you're really doing is changing the order. Okay, you're changing the order. Each way of doing that is called an arrangement. Okay, so that's what that means. But when you combine all of these into a single expression, it takes on yet another significance. Okay, oh, by the way, if you're interested, you can look this up in your calculators. It's in there in a place that we haven't really used so far. There's a menu in there called math. So let's say I want to calculate 3 factorial. Not by doing it myself, but by using the calculator. You would type 3. Let's do this right now. Take out your calculator, type the 3 first. And then you have to find the right menu. There's a math button in the, it's actually the upper left-hand corner. It's the third from the top in the far left column. Once you get there, there's a bunch of submenus. The one you want is PRB, which stands for probability. All right, and then you scroll down to number 4. There's your exclamation point or factorial operator. Hit enter. And then you should see on the screen 3 factorial, hit enter, and it comes back with 6. And that's it, which is good. I mean, with 3 factorial, you know, what's the big deal? I can do that myself. But if you have a large enough factorial, the calculator will be very, very useful. Suppose you wanted instead 10 factorial. Well, that's going to take a long time by hand. So if you do it with your calculator, 10 math, PRB, number 4, enter. Look at that. It's 3,628,800. That's a lot of calculations. So that's why it's helpful to have this on the calculator. Now, if you have one of the other Texas Instruments, like the 89 or the Inspire, you might have to look elsewhere for this information. Okay, I don't really know how those calculators work. So any number you need, you can find it very easily using that math probability menu. But the most important thing is remember to type the number first and then go through all the menus to find the factorial operator. If you do it out of order, you'll not get an answer. All right, so that wasn't too bad, but we still have a little ways to go before we start using any binomial calculations. Because this, like I said, this expression has an important significance. It's not just a bunch of factorials. It's not just a bunch of arrangements. It gives us a very useful piece of information about these probabilities. That's why it's listed separately, by the way. Now, as it turns out, though, I'm going to show this to you in 2 ways. We're going to do it directly by just literally plugging in the factorials, but then it turns out the menus in the math section also make this doable with a couple of keystrokes. All right. So I don't want to jump ahead too far. Those are my examples. So I'll tell you what, since we're done reviewing, and I'm going to see you again on Tuesday anyway, why don't we knock it off right about here? And we'll pick it up again on Tuesday. We'll get back to this discussion, and then, and we can also continue to go over the the sample midterm if we want to, but Tuesday we'll do some more of chapter 6, and then on Friday, March the 4th, we'll do the actual exam. Okay, so all right, I think this is enough for one day. So unless you have any last minute questions, I will just see you next Tuesday, probably in person. All right. So I'll see you all next time. Oh, here's a chat. Oh, you're welcome. Yes, you're welcome.
Thank you.
Thanks.
Okay.
Have a good day.
All right, bye.
Thank you.
Okay, bye.